in that cavity, as long as the distance between the two sides of the GAN is integer times of the wavelength of the light. So what happened is that the low order mode, they'll have a profile like this. Most of the energy is concentrated in the middle of the GAN. And since the photonic crystals are more on the surface, like in this picture here, the low order mode doesn't interact very much with the photonic crystals. So the low order modes are not very well extracted from the GAN. So what they do is that they put an extra layer here in the middle. So this layer doesn't have much effect on the electrical properties, only on the optical properties. It has a lower refractive index. So what happened is that the light that usually would be in the low order mode like this is now split in two lower modes like this, and this one is much closer to the photonic crystal and interacts with the photonic crystal and manages to go out of the LED. For the high order modes, it's already quite spread to the GAN, so it interacts already with the photonic crystals, and the low index layer doesn't have much effect on the high order mode. So here we can see a picture of an LED with photonic crystal and without. We can see that the one with has output much higher, and also we can see that it has kind of a hexagonal shape like this, and this is obviously due to the symmetry of the photonic crystal. So more precisely, the directions like this and this are what we call gamma M directions. So in this figure, this is like a zoom-in figure of a photonic crystal. The gamma M direction is like this, and because it's symmetric, it's also like this, and like this. So later we're going to present some results where we present something depending on the angle, and the angle is always on the gamma M direction. So we put, like, for example, here we put the detector like this, and we move the angle like this in that direction. This is one gamma M direction. So the way the light comes out of the LED with photonic crystal depends a lot on the parameters of the photonic crystals. So these parameters are, first of all, the symmetry. In this one we have a triangular symmetry, and also then we have the lattice constant, which is the distance between two holes. In this article they use lattice constant around 200 nanometers. And then we have the depth of the hole. So on the vertical axis, this is, let's say, GN model like this. So the depth of the hole is also very important, because if it's not deep enough, it won't interact with some modes. So in this article again, the depth is around 100, 200 nanometers, depending if they use ITO, LED, or nickel gold LED. And finally, there's also the fill factor, which is only the area covered by the holes over the whole area, which is related to the diameter of the holes. So now Jerry will explain some more details.
So now I have to talk to you about the reciprocal lattice vector. Because if you don't know what is RL vector, you will got no idea what we are going to talk about. So I will briefly explain this. Reciprocal lattice is not you have the lattice in a real space, right? You do some Fourier transform. You can transform this spatial function into another space that we call it is a momentum space or K-space. And next. So here are some simple math concept of a RL vector. Suppose now you have a plane wave that's exponential I k dot r. Then the k is the wave vector, also the propagation vector. And usually K in the air is 2 pi over lambda. Yeah. And also, okay, oh, I forgot something. If you don't know the transform, I can have some similar things. I believe most of you already take the course of signal assistance, right? So in signal assistance, you use the Fourier transform from the time domain transform to the frequency domain, right? So the transformation here is much similar. It's just from the real space to the K space. Yeah. Okay. So now, if here you have a periodic lattice in real space, yeah, and you can do the transform, and we can see here A1, A2, A3 is the primitive lattice vector of the real lattice, and after the transform, you will also get a periodic reciprocal lattice, and B1, B2, B3 is the primitive lattice vector of the reciprocal lattice. So next one. And because we are talking about what's the condition the light can go through the LED to the air, right? So we have the cross condition here. We have to express it in the RL space. So I believe most of you are familiar with the first formula, right? It's like this. So how we interpret it in the K space? First, you have the K initial, and because the light will interact with the